All right, looks like it's noon, so we'll go ahead and get started. Folks at home, you can hear okay? Is it coming through? So last time we were talking about how it is that we know what we know about organic chemistry. We talked about infrared spectroscopy and mass spectrometry as ways of verifying the presence of certain functional groups and as ways of confirming that you've got the right mass in your product. But we also need a way to figure out what's bonded to whom. Whom is a funny word, actually. Yesterday, Nate and I, Nate is the 18-year-old or 17-year-old anyway. He kind of likes words and puns, and so we were talking about the word to send. You guys have heard this. I think we maybe talked about it in this class, or maybe it was the other one. Full send is like to really go for it or something like that. And then Nate and I were imagining a conversation with a young person saying, "Dude, send it." And then an older person saying, "But to whom shall I send it?" Anyway, and to whom, the young person would of course not know how to use whom. Anyway, sorry. Nuclear magnetic resonance spectroscopy is the way that we can establish what the connectivity of a molecule is. It's heavily based in nuclear physics, but fortunately you don't have to be a nuclear physicist to understand or to be able to use it, rather. We'll cover sort of the basis for how it works at a very superficial level and then get into what kind of information we can get from this set of experiments. So the first thing you need to know is that some nuclei have an angular momentum or spin. And depending on how many protons and neutrons a nucleus has, the nucleus might overall have a non-zero spin. And it just so happens that the proton and actually carbon-13, the isotope carbon-13, both have a spin number of 1/2. Spin numbers can actually be half integral values. They can sometimes be integers as well. We'll focus just on the spin 1/2 nuclei. And what this means is there are two spin states available to each proton. And the spin states we'll call M. So a proton can be M equals 1/2, or a proton can be M equals minus 1/2. And in a lot of ways, this is like the electron. The electron can have upspin or downspin. Okay, so if a proton is not in a magnetic field, upspin versus downspin can't matter. The energy has to be the same. But if you put the proton in the presence of an external magnetic field, which I will represent with that arrow and the letter B with a 0 or a not sure why your text does that, but we'll stick with that. So this is the applied external magnetic field. As soon as you do that, you split the energy of those two states. So now being lined up with the field, let's say being lined up with the field is the M equals 1/2 state, is lower in energy than being aligned against the field. And that energy difference here is something we can measure and exploit. Now, the difference is really small. In terms of energy, it's about 1/10 of a kcal per mole. Recall that the average, carbon-hydrogen bond is in the range of 80 to 100 kcals per mole, and so this is very much smaller than an actual bond. And if you calculate the equilibrium constant, what you would find is there's basically a 1-to-1 ratio of spin states in the magnetic field. Probably it's around 49.999% protons in the against field spin state and 50.001%. Even though the difference in population is in the thousandths place, this energy difference is sizable enough that we can measure it. And if you take that energy difference with the relationship from with Planck's constant and frequency, what you conclude is that the frequency at which you can make a proton go from the 1/2 to the -1/2 spin state is in the range of 3 to maybe 9, depending on the magnetic field, times 10 to the 8 per second. And it's convenient to not use scientific notation, so we'll just convert that into 300 to 900 megahertz. And this is in the radio frequency. I think I'm suddenly hearing the radio station tag lines from the radio, 97.9. I think that's 97.9 megahertz. Who out there went, Salt Lake City? No? Okay. You need to listen to the radio more, I guess. This is in the radio frequency area. And so the idea is, can we apply light in the radio frequency part of the spectrum to cause this transition? Can we see that radio frequency being absorbed, and can we learn something about the proton based on what that frequency is? The size of this energy difference depends on the strength of the magnetic field. And that's important for later on because we will see that variations in the magnetic field that a proton experiences will cause variations in the frequency where the proton can undergo this transition. By the way, going from the lower spin state to the higher spin state, that transition is called resonance. That's the resonance part of NMR, though it's not resonance in the sense that we learned it about resonance structure, so different use of the word. When the magnetic field strength is about 14.1 Tesla, you get frequencies in the range of 600 megahertz. All right. Now, it turns out that frequencies of protons in many molecules vary, but not in the ones place or the tens place. In fact, they vary in the thousandths place. So in general, and just sort of as a rough calculation, proton frequencies might vary between 600 megahertz and 600.009 megahertz or something like that. And so those are inconvenient units to be dealing with. You want to graph something and the numbers are changing here and you're writing all these useless digits. So the way we've chosen to deal with that is to define a version of frequency that gets us to reasonable numbers. So we define chemical shift by taking the frequency of a proton resonating in units of hertz. So this would be 9,000 hertz as an example, that 9's digit. Then we'll subtract the frequency of a reference proton, and then we'll divide that also in hertz, and then we're going to divide that by the sort of, one way to think of this is the frequency of your reference proton, but this time in megahertz. Why would you do that? Well, let's just do some math, but not actually worry about the math. So 600.009 megahertz minus 600 megahertz, all in hertz, is like 9,000 hertz. And then say the reference proton is at 600 hertz. Then you would get the number, 600 megahertz. The hertz units cancel out, hertz, doesn't it? Sorry. And you get 15, basically with the mega prefix in the denominator, which is the same as 15 times 10 to the minus 6. But we don't like that, so we're going to replace the 10 to the minus 6 with parts per million, or ppm. All right, now that we've talked about that, you can promptly forget all of that math and just understand that chemical shift, which will give the symbol delta, is measured in parts per million. And that chemical shift varies linearly with frequency. So higher magnetic field strength leads to higher difference in energy, leads to higher resonance frequency, leads to higher chemical shift. All right? The chemical shift symbol is this Greek letter delta. We use it for other things, but when we use it in an NMR, it refers to the resonance frequency of the proton. Someone from home asks, is this fun fact stuff like terpenes that will kill us on a test if we don't know all of it well, or is it in a study guidebook for us? This is in chapter 14, but obviously it's going to be a bad idea for me to ask a question where you're calculating chemical shift values. I'm not interested in whether you can subtract or divide. But the concepts are important, and we'll talk about how to interpret this NMR data. Why is all of this useful? Principle number one is that chemically distinct protons have distinct chemical shifts or values of delta. They have distinct values of delta because they experience different environments. And what we mean by different environments is they experience different local magnetic field strength. So if one proton experiences a different field strength than another because of factors we will talk about, it will experience a different delta E, a different resonance frequency, and therefore a different chemical shift. So let's talk about environmental factors that can influence the field that a proton feels. Question so far, by the way, we can pause. Yeah?
When you say field strength, are you referring to like the same thing we learned about 106 and 105? How do you know it's
Am I referring to the same thing you talked about in 107? We are going to relate the field. Yeah, the question here is this idea of field strength that a proton experiences related to some things you learned in 107 about nearby electronegative elements? Yeah, we're going to learn how to rationalize what kind of field a proton experiences based on what's around it. The first principle is that electrons influence the magnitude of the field that a proton experiences. And so imagine this dot is our friendly neighborhood proton, and we'll just draw a circle to roughly represent the electron cloud surrounding that proton. Okay, I should have used a bigger marker for that. Oh well. Okay, so one of the things you may have learned in physics is that electrons respond to magnetic fields. I had to look up some stuff about the right versus left-hand rule, and I'm not even going to require you to do this, but in the presence of a magnetic field going in the vertical direction, you will induce current. Physics, weird definition. Current is motion of positive charge, opposite electron motion. I didn't make the rules. Will cause current to circulate in that direction. Okay, so in red is this sort of induced current in the electron cloud. They will move because of the external magnetic field. But one of the other great things about physics is you learned that electrons moving in a circular pathway, or electrons moving in general, generates its own magnetic field. So if you apply the same right-handed rule or whatever to the motion of that current, what you would conclude is that the electrons surrounding the proton generate their own magnetic field in response to the external magnetic field. Oops. And you can predict the direction of that induced magnetic field. Hold on, I got the arrows wrong, didn't I? Look, look, look. You can predict the direction of that induced magnetic field based on where the current is going. So if you look at where the proton is, so this is our induced magnetic field, generated by the electrons in response to the external magnetic field that we're adding, okay? If you look at where the proton is, at that particular point, the field lines oppose the external magnetic field. So we might call this little letter b with a subscript I to mean induced magnetic field, okay? So if we say what kind of field actually, what kind of magnetic field is experienced by the proton, it's not the whole magnitude of capital letter B subscript 0. You've got to subtract that induced magnetic field. We're not going to ever measure that induced magnetic field, but conceptually what that means is protons that are in electron-rich environments tend to generate larger induced magnetic fields in opposition to the external magnetic field. And therefore, protons in electron-rich environments don't experience as much of the external magnetic field. They are said to be shielded from it, and they will resonate at lower frequencies. Let's just make that clear. Let's call the magnetic field experienced by the proton. We'll use the subscript little letter e for experienced. That's going to equal the external magnetic field minus the induced magnetic field. If that induced magnetic field is sizable, then the field that the proton experiences is lower to some extent than the field that you've applied. This means a smaller or lower delta E, a lower resonance frequency, and therefore a lower chemical shift. So protons that are in electron-rich environments are said to be shielded, like the electrons are shielding the proton from the full effect of the magnetic field. All right. Question so far? Yeah.
What was BO and BI again?
B subscript O or whatever is external magnetic field. Although calling it B and O, I mean, suddenly I'm thinking of the gym, so I could have chosen better letters. Yeah. And, oh, I'm sorry, you asked B with subscript I. That's the field that's induced because of the electron motion. Yeah.
Just a quick question. With the induced magnetic field of the electron density, will it ever go in the same direction as the external magnetic field?
Yeah, will the induced magnetic field ever go in the same direction as the external magnetic field? Yes, there are some structural cases. There are only a few of them, but there are some structural examples where that's the case. The classic example of that is in a benzene ring. So we'll just show protons there. The benzene ring is unique because you have this sort of continuous space of pi electrons above and below the ring. I'm just going to show that the pi electrons, this isn't an orbital, this is just showing you where the pi electrons are above and below the ring. If you apply the external magnetic field and then do the same analysis with the right-handed rule and the field lines, what you would show is that the current is circulating in this direction, and therefore the field lines oppose the external magnetic field inside the ring and on the faces of the ring, but actually reinforce the external magnetic field outside the ring. So this proton here actually gets to experience the field that proton experiences is the external magnetic field plus the induced magnetic field. At that position, the proton experiences that induced magnetic field. Now, if you could put something on the face of the ring, you might expect it to be shielded because the magnetic field at that point would oppose the external magnetic field. And there are tons of examples in NMR experiments where protons that are held close to an aromatic ring on the face will be shielded. But for our purposes, we're going to see that protons adjacent to a benzene ring are unusually de-shielded. Okay, so a proton that's in a proton in an environment where the external magnetic field is reinforced by the induced magnetic field, this is going to experience a larger overall magnetic field, therefore a larger difference in energy, a higher frequency, and therefore a higher chemical shift. These protons we will say that they are de-shielded. Okay, now does that help? Now that's not the only way that you can be de-shielded. Alternatively, you can be in an electron-poor environment. So protons in electron-poor environments experience less electron density, and therefore they experience more of the external magnetic field, and they are de-shielded. Okay. Questions so far? Shielded means lower values of chemical shift. De-shielded means higher values of chemical shift. Yeah?
Can you create electron-poor environments for more electronegative atoms?
Yeah, good question. Can you can you create electron-poor environments by proximity to electronegative elements? Absolutely. So a hydrogen on a methyl group will generally have a chemical shift that is near 1 ppm. But if you put that hydrogen alpha to an electronegative atom, suppose like an alcohol, the chemical shift you will observe will be in the 3 to 4 ppm region. So yes, proximity to electronegative elements can cause de-shielding. And you would say that these methyl protons adjacent to the OH group are de-shielded relative to the ones that are just on a hydrocarbon chain. Good. Other questions? So yeah, let me just repeat that for folks at home. Higher chemical shift is said to be de-shielded. And actually, people will also talk about higher chemical shifts as being upfield, because protons in that region experience more of the magnetic field than protons at the lower end of the spectrum. Lower values of chemical shift, I think I'm exactly wrong on that. I always get that one wrong, so don't worry about that. I won't ask you questions about upfield versus downfield. Protons that have lower chemical shift are said to be de-shielded. I'm sorry, said to be shielded. Now I'm all over the place. What we've written here is correct. Shielded means lower chemical shift. De-shielded means higher chemical shift. I'm sorry for the confusion. It is written very clearly in your text, so if you're still confused after what I've read, just consult chapter 14 and it will tell you the way things really are. Yeah?
Are the terms shielded and de-shielded relative to, I guess, certain, are we doing it always in comparison?
Yeah, it's a great question. De-shielded and shielded are relative terms, so they're always in comparison to something else. So yes, we would say the protons adjacent to the OH group are de-shielded relative to ones that are not adjacent to an OH group. In most of these experiments, we have a reference compound that tends to resonate at a fairly low frequency. And so you can always talk about being shielded or de-shielded relative to the reference compound. Yeah?
There's like shielded or shielded that have anything to do with like electron shielding, with like bigger atoms and everything on the electrons.
Does the shielding or the de-shielding have to do with, say that one more time, please.
With like electron shielding. So you have like
Oh, with the concept of electrons being shielded from the nucleus by inner core layers? No, it's a different phenomenon. Yeah, okay. So I thought maybe others, anything else? I thought maybe it'd be useful, your text shows you some tables and we don't necessarily need to reproduce all of it, but I thought I'd show you the kinds of chemical shifts that you can observe for common functional groups in organic chemistry. This is going to complement what you get from infrared spectroscopy. So I already mentioned alkyl groups. If you're on a primary carbon, the chemical shift tends to be at around 1 ppm. If you're on, and it changes, and I don't necessarily see this as terribly important to memorize. You're always going to have access to a table of these values. On a secondary carbon, it tends to be about 1.3, and if you replace one of those H's with another alkyl group, it gets around 1.7 ppm. So those are for alkyl protons. And we'll start sort of at the low end of the spectrum, and we'll move to higher values of chemical shift. Next come protons that are alpha to a pi bond of some kind. So there are a lot of ways you could be alpha to a pi bond. As an example, here's a carbonyl. You could be at the alpha position relative to a carbonyl. Alternatively, there's another functional group you might not be aware of. You'll learn about it in 352. You don't have to memorize it or anything. It's called an imine, but there is a carbon-nitrogen pi bond, and if you're at the alpha position, you also tend to show up in this region of the spectrum, 1.5 to 2.5 ppm. Interestingly, you can show up in this area of the spectrum too if you're just alpha to a regular ordinary everyday carbon-carbon pi bond. And also if you're alpha or on a carbon that's attached to a benzene ring, again, alpha to a pi bond, you tend to be in this area of the spectrum. Though if you're alpha to a benzene ring, you might be even just a little higher because of that de-shielding effect that we talked about. Okay. Questions so far? So some functional group pattern recognition is useful here. Another very useful region of the spectrum, as we just talked about, is if you're alpha to an electronegative atom. So classic examples of this would include being alpha to an OH group or to an amino group. The squiggly lines here represent other things, typically alkyl groups. You could be alpha to an electronegative halogen like fluorine or chlorine, and the chemical shift value is going to be in the 2.5, but usually closer to 3 to 4 ppm area. All right. How about the proton that's attached to the alcohol? Well, that gets a little tricky. Alcohols and amines have these hydrogens that are on electronegative atoms. And as you know from earlier on in the course, these kinds of groups can hydrogen bond. And the hydrogen bonding process tends to alter the resonance frequency and maybe spread it out quite a bit. So depending on the situation, peaks for protons directly attached to heteroatoms can be broad, meaning not sharp. And then another thing is that they can disappear in certain solvents. We haven't talked about what solvents we're using for NMR experiments, and we can come back to that a little bit later. Going further down the list, you've got vinyl protons. So these are protons directly attached to carbon-carbon double bonds. Those tend to show up in the 4.5 to 6 region of the spectrum. The functional group that your book doesn't talk about, but that actually is fairly important in biochemistry, is the amide proton. So this is a proton attached to a nitrogen where the nitrogen's bonded to a carbonyl oxygen. This shows up in the 6 to 8 region of the spectrum, and the peaks tend to be sharp but they can also disappear in certain solvents. And some chemists use that as a way of assessing how strong certain hydrogen bonds are in biomolecules. Benzene ring protons, we'll call those aryl protons because they are arenes, they are aromatic conjugated alkenes, show up in the 7 to 8 area of the spectrum for reasons that we talked about. And then the last couple of functional groups are the aldehyde, where the proton's directly attached to that carbonyl carbon. That's 9 to 10. And then a carboxylic acid tends to be in the 10 to 12 region of the spectrum. What I said about alcohols also applies to carboxylic acids. Those peaks can be broad and they can sometimes disappear depending on the solvent. Okay, so some good questions from the chat. If I have a molecule with multiple functional groups, how do they measure the chemical shift? So first off, each proton in a molecule is going to show up, each unique different proton is going to show up at a different chemical shift. But yes, a proton that is adjacent to multiple functional groups will have, those functional groups will affect that proton's chemical shift. As an example, if you were, say, a proton in between two carbonyl groups, you know, I don't know what the NMR spectrum of this molecule is. We could look it up. It's known, definitely. But you would expect these ones that are alpha to 2 carbonyls to have higher chemical shift than the 2 methyl groups. The 2 methyl groups, you'd expect chemical shifts around sort of 2 to 2.5 because they are alpha to a carbonyl. The ones in the middle would experience both of those effects. And they are, to some extent, additive, but making that kind of detailed analysis will be beyond the scope of this class. So how do you know where on the molecule you have the OH group in a molecule with a given molecular formula? In other words, what if I had something like this? How do I know whether it's this group or that group, right? Great question. There's actually more information in the NMR spectrum that we can use to get all of these details. But before we talk about that information, now that we're used to the idea of different kinds of protons resonating at different frequencies, I want to just briefly review something that you probably picked up in Chapter 5, which is how to tell whether, based on a structure, whether protons are different or not. Because this is good to know because then you can predict how many NMR signals you should see in a spectrum. So let's just do a little quiz without consequences. What protons are identical? Okay. Benzene ring. C6H6. How many different kinds of protons do I have? Just one? Okay, how do you know that? It's true, but how do you know that? A little bit louder. I'm getting old. Every bond in the ring is the same? Okay. So one thing we know about benzene actually is that it's represented by 2 resonance structures. It's not like this is a double bond and this is a single bond. Instead, every carbon-carbon bond in that ring, regardless of the cruddy way in which I've drawn it, is equal. Yeah. And you're right, there is only one kind of proton. We'll shade in the same colors the protons that are equivalent. The principle is that protons that you can interchange via a symmetry operation, and by that I mean mirror or rotation, are identical, right? So all I would need to do to trade one proton on benzene for another let's just pretend we thought this one was different. All we'd need to do is copy, paste, and then, hold on. If I draw the box, I can rotate in a controlled way. Same, right? Alternatively, you could note that there is a plane of symmetry here that makes these two protons equal to each other and these two protons equal to each other, and you could make that conclusion. Okay, let's maybe make it a little bit slightly more challenging. Let's do the following simple molecule. By slightly more challenging, I mean ever so slightly. How many different kinds of protons do I have there? Just one, again, because we can trade places of those protons by simply rotating around that carbon-chlorine bond, right? If by rotation you can interchange the position of protons, then they're identical. In general, at temperatures that we're interested in, where rotation is possible, protons in a methyl group will be identical to each other. All right, we're maybe getting bored. And if you are, that's good, if you get the answers right. How about here? How many different ones do we have there? What do you think? 2? Okay. Which ones are identical and which ones are different?
The methyl hydrogens are the same.
Methyls should be the same. You can interchange them by rotating around this axis or by reflecting through a mirror also right there. Oops, that was the eraser. And then these two, are these two the same or different? Also the same, because you can interchange them by taking the molecule and pancake flipping it, right? The pancake flip is useful. Doing that would show you that these two are the same and these two are the same. Similarly, the board itself is a mirror plane that would reflect the proton on top with the proton on the bottom. Okay. So in some cases, CH2 protons are identical to each other. Is that always the case? Well, before we do that, let's just consider a simple alcohol. How many different kinds of protons? 3. 1, 2, and then 3. Yep. Now, so far that's good, and that will steer you right most of the time. But we need to consider a case in which we have a stereocenter. All right, let's walk through this bit by bit. The proton that's on the alcohol should be its own thing, clearly. And the CH proton that's adjacent to that alcohol on the alpha carbon should be its own thing. Oops, I wanted different color. How about the methyl groups on either end? Are they the same or are they different? Ah, controversy. Some said same, some said different. Well, you're right, it is different, but we want to help people that said same. So why are they different versus same? You said same, but you withdraw, Hiram withdraws the assertion. Okay.
I said it was different because it's the methyl group on the left side is closer to the oxygen, and it's alpha.
Right.
It's beta.
Right, yes, the methyl group on the left is beta to the alcohol, whereas the methyl group on the right, I guess, would be gamma to the alcohol. Yeah, there's no symmetry operation, flipping things over, reflecting, rotating, that could bring this methyl group to be equal to that one. So they have to be different. Now, if they're chemically different, that doesn't mean that their chemical shifts will be dramatically different. One may be at 1.1 ppm and the other might be at 1.2. They might even overlap a little bit. But they are chemically different, and so there's a chance you could observe them both at different spots. So we'll make those different colored. Now, the hard part is these CH2 protons. Okay? Remember, in order to be identical, you have to be able to interchange them via a symmetry operation. So let's just remember above in, let's see, this molecule, the board itself was a mirror plane, right? The proton here was above and this one was below. What about here? Let's let the board itself be the mirror plane. Does the up proton, which we will call A, reflect accurately into the lower proton, which is B? Oh, sorry, a question from the chat. Yeah, Kiana, in this previous one, the board is also the mirror plane. HA equals HB here. Okay, are HA and HB the same? Do they experience the same environments? No, they can't. HA is on the same side as OH, whereas HB is on opposite sides as OH. So they can't be exchanged by a symmetry operation. Now, you could say, well, haha, evil Dr. Price, I know that I can rotate around carbon-carbon bonds, so let's rotate around that bond and let's bring methyl group here and the other methyl group there. Ah, now we have the OH group here and proton here, but HA is still here and HB is still there. Are they the same yet? Still different environments, right? Now, proton A is on the opposite side as the OH group, and proton B is on the same side as the OH group, but there's still not a symmetry operation that makes them experience the same thing at the same time, okay? Those two protons are chemically different. So this is generally true in chiral molecules. CH2 groups, and actually any groups that are the same but attached to this, well, any groups that are attached to the same carbon, CH2 protons are different in a chiral molecule. We have a word for CH2 protons that are different in a chiral molecule. The word for that you encounter in your text, and you will definitely encounter it again when you take the Organic Lab 353, is the adjective diastereotopic. These protons are diastereotopic. Topic means shape, and diastereo refers to diastereomer. The idea here is that if we pretended that we could label proton A with something like the letter A, and then instead chose the other proton and labeled it, pretending for a moment that we could tell proton A from the other unlabeled one, these two options would be diastereomers, right? Maybe to make it clearer, let's imagine we replace proton A with some group in our heads just to determine whether it's in a same or different environment. If we do that, those two options are diastereomers. Okay, so protons that are not interchangeable by a symmetry operation are different. That means plane of symmetry or rotation. And then CH2 groups in chiral molecules are different from each other. Yeah?
Just to confirm, so those two hydrogens on the CH2 will have different peaks when you do the hydrogen magnetic.
Yeah, so the question is, if they are chemically different, will we see two different peaks for those protons? And the answer is we might. It depends on the molecule. There's the possibility that they might have different frequencies of resonance. They accidentally might have resonance frequencies that are pretty close to each other, so there might be some overlap. But actually, in many cases, especially the closer you are to the stereo center, there is a pretty sizable difference between those two. And so you can tell those situations. All right, others? Yeah.
Does that mean that ppms are different?
Yeah, that means they're chemical shifts. So they are diastereotopic. They would have the potential for different chemical shift values. If protons are identical, they must have the same chemical shift. If they're different, they can have different chemical shifts, though depending on the situation, there might be some overlap. Yeah, Byron?
Does it matter if, like, there's a lot of the same types of protons? If you have a bigger molecule, like a polymer or something, and it has a lot of the same atoms or the same types of hydrogens that all like go together,
Yeah.
is that, like, how does that affect ppm?
Yeah, so the question is, if you have a molecule where there's a lot of similar kinds of hydrogens, how will that affect chemical shift? In a molecule where there's not that much difference in the overall environment from one proton to another, you will start to see peaks overlap with each other. The NMR spectrum will get complicated and impossible to interpret. So obviously, we're not going to ask you to solve the structure if it can't be solved. Yeah. All right. Anything else? Yeah. How would you see the chemical shift for a triple bond? I left that one out. That one is kind of weird for reasons that we don't necessarily need to discuss. The being attached at the position, being attached to a carbon that's involved in a triple bond, if you're attached to a double bond, you're vinyl. I'm not sure what the word is for directly attached to the triple bond, so sorry about that. But yeah, that chemical shift tends to be about 2.5 ppm. Your book talks about why that's different from being attached to a vinyl proton. It has to do with ring current, but not necessarily in a way that you need to know or be able to reason through. All right, other questions? All right, so you can look at an NMR spectrum and tell how many different kinds of protons you have. And the reason you can do that is because different protons experience different environments, different extensive shielding, in a way that generally follows the patterns shown here. But that's not enough usually to tell you the difference between, say, isopropanol and ethanol. And that difference could be important to know. Now, I suppose if you had a bottle of clear colorless isopropanol and a bottle of clear colorless ethanol, you might want to know which was which. If you were at another institution, had not signed the honor code, were not keeping certain covenants, you would want to drink one but not the other, right? I told you about my friend in grad school that got sick, got the stomach flu, and he decided he needed to disinfect his drinking glasses for whatever purpose. He did it with rubbing alcohol, but was so sick he just let it soak in the rubbing alcohol, got up in the middle of the night to get a drink, took a taste of the isopropanol, and fortunately did not ingest a lot of it. So knowing the difference is useful. How could you tell? How can we tell the difference in terms of the NMR spectrum? It will turn out that the field experienced by any given proton is also influenced by protons that are nearby. Okay, so I just want to start this, and we'll have to pick this up a little bit next time, but I want to start with a situation where we have proton A and it's adjacent to proton B. Those names are kind of boring, so I suppose we could give them proton Anakin and proton Sheev. Nobody knows who Sheev is. He says, I am the Senate. Sheev, the Senate, Palpatine. Anyway, proton A and proton B. Both of these are magnets, right? Both of these experience the external magnetic field, but they each have their own magnetic field that can influence nearby protons. So let's imagine that we're asking what resonance frequencies proton A can have. There are two different environments proton A can experience, right? Proton A can experience the external magnetic field plus the little field that Sheev contributes. Or there might be an analogous situation in which proton A for Anakin experiences the external field that is opposed by the mini field that proton B experiences. two different possibilities for what proton A can experience, two different frequencies at which it might resonate. We'll pick that up next time.
Is it a spin-off, I guess, from hyperconjugation?
It's related to